My dear students and learners, welcome to my 15th video of Engineering Thermodynamics for second year mechanical engineering students, and I am covering first unit in the Anna University syllabus. And now in this video we will discuss study flow devices. As a continuation of last two videos, I have been discussing about study flow processes, study flow energy equation and study flow devices, how that study flow energy equation called SFE equation is being applied to various study flow devices, especially thermal devices, and what was the outcome, how to reduce the equation, SFE equation for various applications was taught or imparted to you in the last two videos, and now I am continuing and applying the same concept, SFE concept, to other devices also. So here in last video we have substituted the SFE equation for compressor, turbine, etc. And now we are moving to the application of SFE to condenser. Okay, condenser is a thermal device, or it is a type of heat exchanger equipment. Okay, what is this heat exchanger is? This is the device which is used to transfer the heat from one fluid to another fluid. Okay, so of course it is also working under thermal conditions only. Okay, so condenser also you can able to see in your refrigerator which is available in your home. At the back of the refrigerator you can able to see a small motor like sub device is called a condenser. Okay, so here it is used to transfer the heat from one fluid to another fluid, and no mechanical work, that is condenser is not concerned with any work, or we are not expecting any work from it as turbine, and no change in kinetic and potential energies. No external heat interaction, like we are not supplying heat, supplementary is not there. And only so now we will first write, always I told you that it is good to write the full version of SFE and then reduce one by one according to the data and the purpose of device. Okay, so here you can neglect since absence of kinetic and potential energy means we can neglect G Z1 V1 squared by 2, G Z2 and V2 squared by 2, and we are not expecting any work from the condenser, so W is also absent here, and remaining thing is you will get only H1, H2 and Q terms. What is this Q is? Why here Q has been included in the final form is, I already told you, this heat present in one fluid has to be transformed to another fluid. Okay, so enthalpy of one fluid would be reducing and another fluid would be increasing. Okay, so Q is equal to H1 minus H2. Okay, H consists of U plus P1 V1. Of course, flow energy would be a vital part in all the thermal equipments. Okay, now it is for boiler. Boiler means immediately you know it is used to convert the water to steam, that is phase change has to occur, that much amount of heat and energy has to be supplied to the device. So water is coming in and it is going out as steam. So this is your control volume. You have to write the SFE equation with all the terms, and then if we want to reduce, here we are not working any we are not expecting any work from the boiler. Only thing is the enthalpy should increase by the supply of heat. Okay. So here regarding the altitude and the velocities, if the data have been given for various altitudes and purpose, means you can apply, or otherwise simply you neglect PE and VE terms. So finally you will be getting that is here Q heat supply plus initial enthalpy of water will become enthalpy of steam. Here in the outlet you will get the energized form, energized outcome. Okay, because you are supplying the heat, that heat is added to the enthalpy of water. That's what increased enthalpy steam will come out as outcome. Okay, so if you know the purpose of each and every equipment, it is very quite simple to follow the final forms of the equations. Okay, a turbine, as already we have discussed, write the full form of SFE, and this device is particularly designed for getting the output. How we are getting the output work is by the expansion of the heat energy or reduction of the heat energy of the fluid. In boiler, the fluid or the water is energized by the supply of heat, but in turbine, the steam, the hot, high temperature, high pressure steam is losing its energy, losing or giving the energy to the shaft, and then it is coming out as unenergized water. Okay, so the fluid leaving the system would be lesser energy in turbine, but in the case of boiler, fully energized fluid will come out as outcome. Okay, so here also you'll be getting this work is equal to change in enthalpy. Nozzle, as already I have explained, final version is we will get only enthalpy terms and the velocity terms. So final velocity would be equal to difference in enthalpy, plus if V1 is given in the problem, you can substitute, or otherwise you can just neglect it. And pump of course, like fan, pump and compressor, all are power consuming equipment, and here the altitude will be given as a very important thing, and GZ1 and GZ2 will be present, because the pump will be working from the surroundings and it will give the power to extract the water from the sump to the water tank or over tank. Okay, so the pump is running because of the supplementary of power electrical energy. So here work is having the negative sign. Of course, it is not a product, it is the input here, work. And then change in velocity also, if it is given, you can able to include it. And Z1 Z2 come into play, since here altitude difference is existing, and then you can write the other terms like that, and final version will be coming. Okay, throttling device is it is also like now we can see free expansions and paddle wheel work like that. It is also an irreversible expansion process in which this expansion of fluid takes place from higher pressure to lower pressure. Of course, when the fluid across a restriction or any valve or a small orifice, it occurs in such a way that always it has to maintain the inlet and exit enthalpies as same. Okay, so the fluid exits at a reduced pressure. Here no mechanical work is expected, no heat loss, no change in KE and PEs. So finally you will be getting H1 equal to H2, that is equal to CP. H can be written as CP T1 and CP T2. H1 equal to H2, so T1 equal to T2 also can be applied. Okay. So now let me recall the videos uploaded for first unit of engineering thermodynamics. In my first video and 2 to 3 videos, I discussed about fundamentals of thermodynamics, importance, how the thermodynamic terms has come and joined together, what is the purpose of this subject. And in the next 2 to 3 videos, we have imported with what to tell, the basic terminologies like a system, types of systems, boundaries, kinds of boundaries, surroundings, how they were reacted, what are the importance of open system, and properties type processes, types of processes, various kinds of proper processes, and what is the various variables to be constrained during that processes, what happens when each and every processes takes place at a particular condition. And then now next we studied about in the other further videos, you are imparted with quasi-static process, that is each and every state of the process should be equilibrium. Equilibrium means thermodynamic equilibrium, that is it consists of thermal, mechanical and chemical equilibrium. Simultaneously it has to satisfy, like it should not react with any other thing, it should be stable with that parametric properties. Okay, so it is one of the very important concept. Why? Because no, we are thinking that all the processes whatever we are studying could be able to draw in PV coordinate only if they were in thermodynamic equilibrium condition. Okay, that was the importance of quasi-static process. And then we moved to zeroth law of thermodynamics, in which it was the basis for temperature measurement by using a datum device or a fundamental reference point by which we are measuring the temperature. And another one more object should be calibrated in such a way that it can able to measure all the other body's temperature. And next we moved to first law of thermodynamics. Before that we also studied the types of energies, very important, heat and work energies, how they are working when they linked into a system. Their boundary phenomena, path function, in inexact differentials, and the forms of the energies is being changed when the heat or work is interacting the system. Okay, when they were in the interaction or when the process is going on, at that time only they have their own identity, otherwise they will not be manifested. And first law of thermodynamics for a process and a cyclic process. Next, first law equations is cyclic integral of del Q is equal to cyclic integral of del W, and if it is for a process, dE, difference in energy, is equal to del Q minus del W was arrived, and this equation was used to find out the heat transfer, work done and change in internal energy for various processes like isothermal, isochoric, isobaric, adiabatic process, polytropic process, and reversible adiabatic or isentropic process. And we have also derived all the equations for these processes because problems will be expected from these topics. And then we moved to what is steady flow, what is flow, why that flow is important in the control volume and control surface concepts, what is the importance of open system, when open system why H is coming, for closed system why U is coming, everything was explained. And finally by mass conservation equation and energy conservation equation we have taken a control surface, and then we have derived the steady flow energy equation. And that steady flow energy equation was applied to various thermal devices in such a way that final versions have been modulated to accompany what is the purpose of the devices, what is the inputs, what were the outcomes, okay, of from that devices was imparted. And now I hope that I have done a systematic way of uploading the explaining the videos to the maximum extent how you catch it. I hope all the best, and we will meet you in the next video in the